Hey, welcome to the Explainer. Today, we're tackling one of the sneakiest, most critical topics in embedded systems, RTOS memory management. If you get this wrong, your project can just die, and you'll have absolutely no idea why. So let's just jump right in. What is that one thing, that one problem that causes these mysterious random crashes and resets that are a complete nightmare to hunt down? It's the kind of bug that hides for weeks, maybe months, and only shows up at the worst possible time. You guessed it, it's memory mismanagement. It's not some flashy, obvious bug, it's a quiet one. But seriously, understanding exactly where your data is stored is the key, the absolute key to stopping those catastrophic stack overflows and memory leaks before they even start. So here's how we're going to break it all down. We're going to start with the hidden dangers, then map out the three big memory regions. After that, we'll see how an RTOS just changes the whole game, look at how to choose the right tools, and then get into solving the most common bugs. And of course, we'll wrap up with a little challenge for you. Okay, first things first. Before we can even begin to talk about RTOS specifics, we really need a super clear map of the three fundamental memory areas you'll find in any standard C program. Seriously, this is the foundation for everything else we're going to talk about. So, first up is static memory. Think of this as permanent storage. Before your program even runs, the compiler looks at all your global and static variables and says, okay, I need exactly this much space. The second your device boots up, that block of memory is set aside and it just stays there, totally unchanged for as long as the program is running. Next up, the stack. You can think of this as the system's short-term memory. Whenever you call a function, all of its local variables and arguments get pushed onto the stack. And then, the moment that function returns, they're automatically popped right off. It's super fast, really efficient, and the best part is the compiler handles it all for you. And number 3, we've got the heap. Now, the heap is different. It's this big, flexible pool of memory that you, the programmer, get to manage by hand. You have to explicitly ask for a piece of it using something like malloc, and then you are totally responsible for giving it back when you're done. This is where you get a ton of power, but it's also where the real danger is. So if there's one thing to take away here, it's understanding the different jobs these three regions have. This slide just lays it out perfectly. Static memory is for the entire life of the program, and the compiler handles it. The stack is temporary, for just a function scope, and again, the compiler's got it. But the heap? Well, the heap is all on you. Okay, now for the really interesting part. Let's see how this whole picture changes. Really changes when we bring a real-time operating system into the mix. This is where that simple memory map gets a fascinating new twist, because an RTOS completely flips how we use the heap. You see, in a normal C program, you get one stack. That's it. But in an RTOS, every single task you create gets its very own private, totally separate stack. So where does that memory come from? Well, when you call a function like xtaskCreate, the RTOS kernel immediately turns to the heap and carves out a chunk of memory. That chunk becomes the task's stack and its task control block, or TCB, which is basically how the OS keeps track of everything. This is a huge shift in how you need to think. The heap isn't just for your own data anymore. In an RTOS, it becomes central command. It's where the operating system itself stores all the task stacks, plus other critical things like queues, semaphores, and mutexes. The health of your heap is literally the health of your entire system. Now, because the heap is so incredibly important, a good RTOS, like FreeRTOS, doesn't just give you one option for managing it. No, it gives you several different schemes to pick from, and each one comes with its own specific trade-offs designed for different kinds of projects. And what's really cool here is just the range of choices you have. On one end, you've got Heap 1. This is for those super critical systems where you can't risk a memory leak, so you're not even allowed to deallocate memory. And then on the other end, you have something like Heap 5, which can manage memory that isn't even all in one piece. But for most people, Heap 4 is the go-to choice, because it actively fights against fragmentation by stitching free blocks back together, which keeps your heap way healthier over time. All right, enough theory. Let's get our hands dirty. We're moving from the concepts to the code, right into the trenches. So how do we actually spot, and more importantly fix, the two most common and destructive memory bugs out there, stack overflows and memory leaks? Ah, yes. If you've ever used an ESP32, this site probably gives you chills. But this isn't just some random crash, it's actually giving you a clue. That stack canary is a safety feature. The OS puts a special value at the very end of a task stack. If that value ever gets overwritten, it means your task tried to use more memory than it was given, and the OS steps in and shuts it down to prevent total chaos. So, fixing it is actually a pretty logical three-step process. First, you've got to analyze what your task is doing. How big are its local variables? What functions is it calling? Add that to the RTOS overhead. Second, do the math. In this case, say it's 768 bytes of overhead plus a 400-byte array. So we need around 1,200 bytes minimum. Step 3, go back to your xtask create call, increase the stack size, and always add a little extra as a safety margin. Okay, so the second bug, the memory leak, is way sneakier. It doesn't cause a big, loud crash right away. No, this is a slow death. It happens over minutes, hours, maybe even days, as your code keeps allocating memory, but forgets to give it back.
Let's watch this happen in slow motion. So, when our program starts, we check the available heap. Everything looks great. We've got 250,000 bytes free, plenty of room to do whatever we need to do.
Now let's say we're inside a loop, and we make just one call to PV port malloc for 1 kilobyte. We check the heap again, and yep, just as we expected, our available memory has dropped by a little bit. No big deal, right?
Wrong. Imagine that loop just keeps running and running and running. Each time it grabs another 1K chunk, but it never lets go of the old one. The available heap just keeps shrinking, relentlessly, second by second, until we're down to a dangerously low level like this.
And then it happens. The next time our code calls PV port malloc, the system can't find a block of memory big enough, so it returns null. Our code probably wasn't expecting that to happen, tries to use that null pointer, and bam, the whole system just grinds to a halt or crashes completely. The fix is so simple in theory, but it is absolutely crucial in practice. This is the golden rule of dynamic memory. For every single malloc, for every single allocation, you must have a matching free once you're done with that memory. It's a pair, always. Okay, so we've covered the map of memory, the big RTOS difference, and how to squash the most common bugs. Now that you understand the concepts and you know the dangers, there's really only one thing left to do. It's time to put all this new knowledge into practice. So here's your challenge. Can you build a simple serial echo program using 2 tasks that correctly allocates and frees memory from the heap? You'll have one task that listens for input and allocates the memory. Then a second task will print the message and, most importantly, free that memory. This is the perfect hands-on exercise to really make sure you've mastered these silent killers. Good luck.